Hello and welcome to Extreme Academy Live. This is where you come to advance your knowledge, advance your skills and advance your future. Thanks for advancing with us. Now this is week 5 and the team have told me that potentially we're going to finish at week 7. So we planned in 8 episodes into this YouTube series, but it's looking likely that we're going to land and finish in week 7. Now, if that is the case, if that does happen, we'll make sure that when we get there, we clearly label up week 7 as the final episode. So you know that we're finishing there. And obviously we'll talk about it in episode 7 as well, because that's where we'll tell you how to get access to the certification exam, and that's great news. It means we're 1 week closer to that, and that's what it's all about. This is about learning new skills, then certifying that knowledge and those skills, and getting a badge from Extreme Networks that you can put on your CV, on your resume, and show your current or future employee that you're somebody worth investing in because you're investing in your knowledge. So that's what this is all about. Now, this week, we're talking about something that we're really fond of, we really love here at Extreme. That's networking fabrics. Now, we're really good at that. We've got some amazing technology, but there's a concept there that we want to share with you that's essentially saying that, in the past, networks were built in a certain way. And that's what you've learned about all the way through these courses. But there is a new way, and that's really important when it comes to big networks, because simplicity is really, really important when you get to bigger networks. Simplicity of operation is what I'm talking about. So to do that, to talk about that, Isaac's bringing in a guest. It's David. He's actually lives quite close to Isaac. Here in the UK right now, when we're broadcasting live, we've still got some restrictions on where we can go and who we can meet, but we were okay to have Isaac meet up with David up in Cambridge. And they're going to talk about networking fabrics. And I also want to give a big shout out to David, because he developed some of the curriculum that you are learning about now. So you're going to meet another member of the team that's been working on Extreme Academy behind the scenes. All right, so I think Isaac's going to finish off from last week's episode. Then they're going to get into fabric. I'm looking at Isaac. He's ready to go. I'm going to hand over to him. He's got something new on his shelf. Looks like Isaac. Looks like you got something new for Christmas. Over to you, Isaac. Enjoy the episode, everybody.
Thanks, Rowan. Yeah, that's a little gift that I got for Christmas. Pac-Man. Oh, dude, he's so cool. Listen to this. That's fantastic. I was a big fan of Pac-Man. Anyway, hi everyone, and welcome again, as Rowan said, to Extreme Academy 5. So if we're going to do a very brief recap of where we finished last time, we were talking about quality of service. And sorry, let me just set that quickly, the timer there. So we're talking about quality of service, and the course is about scalable, massive, robust wireless networks. And the types of organizations that build these are large enterprises and ISPs, especially ISPs. And so they build these large enterprises, and then one way to monetize the management and all of this of these enterprises is by offering the quality of service. And I use the example of sending a letter to South Africa, right? In the UK, you send a letter and it's going to get there the next day. It's so great. In South Africa, you send a letter and you hope that it gets there sometime. But if you really wanted to guarantee, that it gets there at the time, you could either pay for premium delivery, or if it was so important to you, you would use a courier, right? A courier, UPS or DHL, one of these, and they might come and pick it up from your premises, or you drop whatever it is at their premises, and they then make sure that it gets on a plane and it gets to its destination at the point in time that you wanted it to be there. You pay more, but you get that service. So enterprises are going to be requiring that type of service, for whatever it is, and ISPs will then charge them accordingly. So it's a business model, the DiffServ, differentiated services a model. And so we covered that. That's what we did. We didn't just cover that, but that was kind of where we landed last time. And this was the particular slide that we landed on. So the differentiated services, we used analogies and we showed how, but it describes, services associated with traffic classes. Now, again, this is a new word, traffic classes. Traffic classification, conditioning, and so we get this term we call or abbreviation that you're going to see quite a bit called DSCP. First time I saw it, I had absolutely no idea. DSCP, and it stands for Differentiated Services Code Point. Differentiated Services Code Point. DSCP, and this is a conditioning, a massaging, an application of a certain sets of conditions that happen at the network edge. So when you enter into a network, be it your ISP, be it your home network, be it your corporate network, when you enter into that particular network, DSCP will kick in and it will actually apply, it will actually apply to every packet that's coming from that particular source. So if that source is identified, for example, on a VLAN or whatever, for the nature of the traffic, whatever it might be, it gets this classification. And that classification, DSCP, is then applied to every packet that's going to be coming in for that particular classification. Okay, so we're going to kind of break it down now. We'll get into more detail, but at the ultimate edge of this is the ability to scale, to provide scalability for our customers. So let's look at this slide now when we're talking about quality of service, QoS, where we talk about classification and marking. So in this instance, the classification is the identifying of the traffic, the identifying of the type of traffic coming in, and then the splitting of traffic into different classes. So the way I kind of think about this as an analogy for me is the following. When I moved from South Africa to the UK, it was quite interesting to me to see that when I one of the first trips that I took in a taxi, I noticed that on the highway, there was a lot of traffic. There were 4 or 5 lanes of traffic, and the traffic was quite heavy. But taxis just kept flying past us on the left-hand lane. And I said, why? How come? And they said, because that lane is specifically for taxis and buses. It's like a public transport, if you want, a public transport lane. And that's kind of what it is, right? You might have multiple lanes, this bandwidth, this highway that's sitting there with multiple lanes, but in this case, classification or the identifying that particular vehicle is a taxi. Therefore, we will take that taxi and we will place it in this lane so that it can flow a lot higher. And so, if you use that analogy for the rest of this. For the rest of these slides that we're going to be talking about now, then you can see that you identify the traffic and then you prioritize the traffic. And that will be done on agreed corporate policy. So corporate would say, look, it's really, our business is all about video conferencing, whatever it might be. Our business is all about that. So we really have to have this as an absolute priority. No matter what else is going on in the company, this needs to have its own traffic lane. Okay? And this is the kind of stuff that we're talking about. So layer 3, layer 2, we will go through all of these things. You're going to hear another term as well, and they sound quite the same. One is QoS, which is the quality of service, and the other one is COS. So QoS and COS, they sound the same. COS would be class of service, the class of service. So you have IP traffic coming in, and IP traffic, just like cars, trucks, and taxis and buses, they can be broken up into these different categories. In this one over here, you can see that I've got 4 classes over here of IP traffic: best effort, transactional, mission critical, and voice. And we'll cover those in a little bit more detail. But quality of service and and class of service marking. How does a packet, how does a switch, how does a device know, that this is a packet that needs to have DSCP marking or has DSCP markings? Well, if you look at the frame, and you look at the 802 here on the VLAN ID, okay, VLAN ID. So we have destination MAC address, source MAC address. This is for layer 2 networking. You can see over here that you have a VLAN ID. Now, we've spoken about this before, because we've said the VLAN ID is like the ability, when you have a virtual LAN, to place users or devices into specific virtual LANs. And this makes segmenting our large network a lot easier. But in that particular field, we have something called an 802.1 Q. Okay, 802.1Q. I don't know if it stands for quality, but it makes sense, right? Quality of service. And in that 802.1Q, we have these over here. Let me just pull up the pen, and there we have these 4 sections, right? And the first one is what we call an ether type value, and that's not to be confused with the same with that one there, which comes in later. This has to come in a little bit before. This one here is not really used anymore because it's generally set to 1 and 1 for Ethernet networks. We have 802.1P, okay, 802.1P. So that's the really important one, because that is a marking. That is the QoS marking that we're interested about. And then that, of course, is the VLAN ID. So here, this is the one that we're interested in, the layer 2 QoS marking, quality of service marking, with a class of service bits, 3 bits embedded within that section. So that's how a device, an edge device or whatever, any device in your network will know. So, okay, I see that in the header of the packet, or in that packet over here, there's that section, and within there it tells me exactly how I need to tag this traffic. So in an IP4 packet header, you can see over here that there are 20 bytes of mandatory header fields, 20 bytes of mandatory header fields, and here you can see, and we can see that over there, right? You can see 8 bits, 16 bits, 2 bytes, plus 16 bits, another 2 bytes, 4. So 4, 8, 12, 16, 20. These are the mandatory, and then you get the optional. But when you look at this, you can see over here that you get the QoS markings. Only the first 3 bits of the IP type. So you're going to see another term over here, TOS, type of service. So only the first 3 bits are evaluated. DSCP, the first 6 bits. So there we go. So that's the type byte, that whole thing over there. But for DSCP, these 6 bits here are evaluated. And Why do we do this? Because we want to be able to have a very granular optimization. So you think again back to my analogy of the highway. You could say, okay, in this highway, we're going to have that one lane reserved exclusively for traffic, for public transport, taxis, etc. Only for that, okay? That's what we're going to do. Now, the rest of the 4 lanes, well, one of them we're going to use just for trucks, another one just for vehicles, another one just for motorbikes, and the other one for, I don't know, something else, boats. No, that would be bad. Whatever, electric cars, for example. It's something to that effect. And in theory, with DSCP, you get because it's 6 bits, you get 63 different classes, or 64 different classes or categorization of traffic classes. So it would be like applying 63 different rules to a highway. You have the ability, but in practice, so even though you have this very wide amount of classes, in practice, in real life, there's generally 4. Okay, there's about 4 that are used on a day-to-day basis. First one is what we call default forwarding, which is basically best effort, right? You've often heard best effort. If you got internet connection at home, it's best effort. It gets there when it gets there, kind of. Then you get the expedited forwarding, okay, which is dedicated to low loss, low latency traffic, something like voice. It's expedited. Then assured forwarding. It gives you assurance of the delivery under certain conditions, under prescribed conditions. And then class selector, which maintain backward compatibility and things like that. So you'll see that there's an enormous amount of granularity, and even though it's there, it's not all used. I mean, 63 classes of traffic, that's really a lot, but it means it's there, okay? So let's think about a little bit now about congestion management, because on that highway, there's congestion. Maybe during 5 o'clock in the morning or 4 o'clock in the morning, coming out of Heathrow, those highways are absolutely clear. You can just motor them. But do that at 8 o'clock or 9 o'clock in the morning, it's completely different. So managing congestion. So the congestion management is about managing each packet to determine which queue. So where am I going to place? Oh, that's a truck. Okay, you're going to be placed here. Oh, that's a tech. Oh, you go here. You're a normal vehicle or a motorbike. Okay, that's where you go. Right. This is what we want to try and do, and it uses. There's sophisticated queuing techniques to be able to do this. And of course, we want to do this because for certain things, for example, voice, it's really important that voice travels on a good line, on a good lane, that's identified as a good class. And for that, a video as well, I suppose, because if it doesn't, if you put voice in together with everything else, you will sometimes break. You get it? I mean, I'm being a little bit dramatic over here, but you get what I'm actually meaning over there. So you want to prioritize that mission critical, mission critical. 40% of bandwidth goes into that particular queue. So this would be your SAP, right? Your SAP, or maybe your email. This is mission critical for our business. Transactional queues. Okay, we need to put a printer. We need to send a job to the printer. Okay, well, I'll get it done when I get it done. It's okay. I know. I'll just put it in the queue. I'll get to it as soon as I can get to it. It will be sorted out. And then your general internet browsing or whatever, Instagram, Facebook, whatever. Yeah. Okay. Just best effort when it gets there, So let's look at some guidelines. If this is an example of the total bandwidth, then you're always going to have this concept of a reserved amount of bandwidth, right? Because no matter how much you've got, you always want the ability, because there will be at in the morning, in the afternoon, when people leave or whatever, lunchtime, people go, they check their personal mail, they go check the football score or whatever it might be. You can't just run 100% of your bandwidth allocated to everything else. You need to have a reserve. So we put, say 20% or 25% as reserved. And then the rest is usable bandwidth. 75% of the total bandwidth is usable bandwidth, right? And then we use the bandwidth reserved for something low latency, right? Low latency. That's low latency classes. That's what we want to do. And there are different queuing systems. One of them was Cisco called CBWFQ, class-based weighted fair queuing. So it's a queuing system. It's not just first in, first out, but it's a queuing system based on classes. And within there are priorities, all right? Priorities of policies. So voice, for example, real-time video voice, that would be within that 75%. It gets a particular priority, right? Its priority is for voice and for video. That's very important. So it knows it's going to have that red lane, where taxis and public transport can travel really freely, even when anybody else is really busy. That's what we're trying to achieve. So congestion avoidance. If you use a GPS and you want to get from point A to point B anywhere near Heathrow on any morning, every option is taken up because there's so much traffic at every route is taken up. So you don't have a lot. But if you're coming out from Cambridge and you're coming in towards London or whatever, it might reroute you. So it might say, I'm going to take you on another route to avoid congestion. Well, in quality of service, when we're talking about DiffServ quality of service, it's not quite the same, right? You have this what we call RED, which is random early detection. So it's also known as random early discard, or early drop, which means that if I know that there is going to be congestion ahead, I can, to prevent me getting into that congestion really quickly, what I can do is I can drop certain packets. Okay, I can drop certain packets because it might ask for a refresh or resend of that to prevent that from happening. So think of it as, if I'm a GPS and I know that there's going to be congestion, I might just say, look, use another completely different route to be able to get to your destination. That's an analogy. It's not perfect analogy, but you have this idea. But because we've prioritized, for example, the voice as a particular class, then what happens in that instance is, let me just set that. What happens in that instance is it's not going to drop packets from voice, because voice has been told, for this type of traffic, we need you to be prioritized. This is very important types of traffic. And then we also get policing. It's not policy. Policing and shaping. And policing drops or marks packets when a predefined limit is reached. So you can set for these DSCP flags, markers, you can set predefined limits on there. So you say, okay, so if this type of traffic gets to that particular level, then you're allowed to drop packets. Okay, so just drop packets. I don't really mind. But shaping says we will shape the queues when preferred limit. So we'll start playing with queues rather than just dropping packets. So for example, if we have a voice, a limit, well, that we don't want to drop anything from there. But mission critical and transactional, well, we can say, when you reach a limit of 200, you're allowed to drop packets. So generally don't drop, but if you reach that particular limit, that threshold, then drop packets. And transactional as well. Under the limit, use, buffered packets. So there's a lot to digest in here. In small operations, small companies, small networks, you probably will not touch that much at all. And so a lot of people who work with smaller networks, DSCP is never going to mean anything to you. But if you work at an ISP, it's really critical, because you're going to be paid according to certain agreements, right? You have to meet a certain level of service. And DSCP is going to be the tool that's going to enable you to do that. Now, how does that work if we use our esports example? Well, we must reduce latency. We must reduce jitter in gaming, right? We need to do that. So screenshot this. I don't want to cover this in too much because detail we've already covered that. Right. I need to announce one thing. Generally, we would do another module on security over here. Now, it's not security as in hacking or anything like that, but just an approach to security called UDA. Okay. I need to end there. Called UDA. Now, that would normally come in here. But I've decided to kind of change it around, and we're going to do something different. We're introducing a guest in this next section because we're going to start talking about fabric and what fabric is all about. All of these things that we've spoken about, how do they manifest themselves within fabric? So I have a special guest, and we'll go to that now. This was pre-recorded at David's home, and I think you're going to find it very, very interesting. And then at the later stage, perhaps the next one is where we'll do UDA. So stay tuned. We'll have a little break, and then we'll go into a day. Or are we going to have a break? No, we're going to go. Oh, we'll have a little break, and then we go straight. Okay, perfect, cool. See you on the other side of this. Cheers. I'm here with David Stooks, a good friend of mine, a good friend of Extreme Networks, a fellow instructor, a very good one, by the way. And I've asked David to come in and do a session with us to cover some stuff that he's much more of an expert at than what I am. So, David, welcome. Introduce yourself to the audience, to the viewers.
Yeah. Hi, everybody. Yes, I'm David Stook, and it's my pleasure. Been working with Isaac for quite a while, and anything I can add value-wise, I'm here to serve.
Very British, very yet to serve. Okay, great. So, David, we've the last couple of material, or the last material that we covered. We did a little bit on quality and service and stuff. Mm-hmm. And so all of that stuff, when you look at it and oversee it, it all makes sense. It all kind of works. You understand it. It's piece. And I suppose when the internet was first invented, when the protocols were first invented, that might not have seemed all the uses. I mean, I remember reading newspaper reports, that the internet would never do video because there was too much email and too much spam, right?
Yeah.
I mean,
I am that old as well, Isaac, so I remember it well.
So, you have these situations where these guys designed a fantastic communication protocol, but they might not have foreseen how this thing would have grown in the years, or maybe to a certain extent. But it kind of feels like, protocols have been added in and bolted on, and to do all of these type of things. I remember going to an ICANN conference, and it was unbelievable that you could have nearly 2,000 people at a hotel for a whole week talking about DNS and IPSEC and just the internet, and
for sure.
ended up with more lawyers than engineers and anything else. So someone once said to me, it's a miracle that the internet actually does work.
Yes. Sometimes we still believe that.
So there's complexity. Let's not kid ourselves, right? I mean, as Academy has grown and as Academy has developed, we've tried to kind of make it really easy for somebody coming in and understanding the basics. And those are course 1, course 2, et cetera, et cetera. Now, we said at the beginning of this course that it starts to get a little bit more scary, right? Because now we start to really get into the routing and some of these really complicated protocols. And it's not easy stuff. You don't come into here if you haven't done the other stuff. It's complicated. And although Extreme Academy, we've tried to be product or vendor agnostic and not talking about ourselves, we kind of now get to a situation where we've got to talk about a technology that Extreme is quite famous for, right? It's not unique to us. Other vendors have it as well. But we need to talk about Fabric.
Yeah.
Right? Extreme Fabric, or Extreme, campus Fabric. And we really need to talk about it because it removes some of the complexity, or a lot of the complexity of having this multi-layer of protocols, et cetera, et cetera. I mean, not that it's, it's a piece of cake. It's still got its complexity, but in managing a network, it's become a lot simpler, right?
Yes, I mean, you're absolutely right, Isaac. As the networks evolve from a sort of nice to have to a must have, limitations became apparent. In response to those limitations, more protocols were developed. And you can almost argue that many of these protocols are just a series of patches to fundamental design weaknesses that from the outset wasn't envisaged. Over time, of course, with that evolution comes, as you say, complexity. So there is an opportunity to look at it again, not fundamentally change the core of the core protocols, such as IP. It's still IP based as a technology, but to look at all the associated protocols in support of that IP endeavor and simplify things. Yes, there's still complexity.
Yeah, sure.
Fabric is certainly a simpler way of doing it, and its success is proven in the field. You're also right, I think, to say, if I may, that whilst Extreme Networks champion Fabric and Campus Fabric, it is based on open standards. So again, staying true to the Academy, we're trying to stay vendor agnostic, and there's very much a vendor agnostic message here.
Yeah. So let's go back a little bit now, and let's talk about large networks, right? And so we've covered before, that networks have, you call them different tiers, maybe, and you have the access tier. So this is probably the tier where most users who don't have a lot of experience would experience a network, right?
It's where we are now.
It's where we are now, right? Yeah. So we this is us. This is us as humans, and we're using mobile devices and computers and all of that. And at some point in time, we are connected in some way to a switch. So this would be what we would just call a switch. And so we would either be physically connected, although today that doesn't happen so much, other than, the big office photocopier and things like that. They're connected via
anything that doesn't physically move frequently. Tends to be still
cameras, that type of stuff, right? So that would be connected via a cable, Ethernet cable. But most of us nowadays home office, whatever, we tether it wirelessly. So it's the same principle. We remove the cable, but we're using radio to do that.
But it's still an access layer function.
Yeah.
Think of the name.
Yeah.
An access point sits at the access layer.
Yeah.
Its primary function is to provide clues in the name.
Yeah.
To provide access.
Yeah. So that's what any large network is going to have, right? This is fundamental to any large network. Now, the next layer up is what we call the aggregation layer, right?
Yeah.
So if you think about this in a building, 3-4 floors, if you have 100 people per floor, you're going to have a number of switches on each floor to handle all of that and all the peripherals and stuff. Mm-hmm. But you then need to connect the second floor and the third floor, and they're both going to have the same type of setup.
Yep.
But all of those packets, all of that data needs to go somewhere, right? And that's where the aggregation layer, comes in. So you would expect on this layer to have switches that are more powerful, more expensive, but more powerful, because they got to aggregate, hence aggregation. They got to aggregate all the data from all of these switches coming in, and in the traditional one, you then have the core or the back one. So these guys are big boys, right? That's those are really big boys that eventually connect out onto the internet.
Pedal to the metal. That's what the core or the backbone is all about.
Heavy metal.
Heavy metal, absolutely. And what you just described there, from access to aggregation, is what is commonly referred to as a building block. Not to be confused with a physical building, but we have a series of building blocks that we then connect into the backbone, the core, to build your campus branch. Think about the core as being something tight and consistent, where its primary objective is to shift bits really quickly from one building block to another building block, and to your point, from those building blocks out to the outside world. A journey we often refer to as north-south or south-north. South being the access layer and north being out to the outside world. Exactly.
Yeah.
Can you see that inherently, and we're talking scaling here, aren't we? You can add additional building blocks to a consistent core as long as the core has been scaled correctly. By scale, has adequate bandwidth to take all of that aggregation from the aggregation layer to shift those bits from one building block to another, or again out to the outside world, the WAN, the internet, to service provider networks.
This model over here, you would generally not see this on a small, medium enterprise, right?
Small mid-market.
They would all have the access layer. That would be there. They would have an aggregation layer, right? Generally speaking, you would need that, but you wouldn't necessarily have the core in a smaller business. This we start to talk about larger enterprise, right?
You're right. In a sense, there is still a core, but it's probably just the cables linking the aggregation switches together. Yeah, and that's often referred to as a collapsed core.
That's what we're looking at. That's what we're looking at on this slide, right?
Yes, indeed.
So where previously you had, I mean, this was us. You had your access, and then you had your aggregation, and then those connected to the core. Now that core doesn't exist. We
can get rid of it. You save money. You lose scalability. But to your earlier point, for smaller businesses, branch offices, smaller regional offices, mid-market businesses even, to go to the cost of what are really quite expensive, generally speaking, core switches, it's not necessary. You've got all the functionality you need. You've got access, you've got aggregation where appropriate. You're still building building blocks, but if you pick the right aggregation layer devices, connect them together, you can avoid actually purchasing these more expensive, yes, powerful, but more expensive core switches.
On this layer, the access layer, here we generally talk in layer 2.
Historically, yes, but I think today we're now increasingly seeing what are called multi-layer switches or layer 3 switches being deployed at the access layer. Why? Because they're typically about the same price. An entry-level multi-layer switch doesn't cost that much more than a simple layer 2 switch. But you have so much more in terms of the services.
The functionality that you have on it.
Yeah, QoS, you spoke about earlier.
Yeah.
The whole OODA story around security. You'll have a richer array of intelligent services when you've got more intelligent protocols at play, which you get with a multi-layer switch. So again, layer 2 historically absolutely dominated the access layer in terms of switches.
No longer.
Today, if you're purchasing new switches today, I'd be challenged to decide, do I just do layer 2?
Sure.
Or do I go multi-layer?
If the price point has come down and they are reasonably close, just the functionality that they give you makes it, even if you don't use it immediately, the ability for you to, as you scale up, to grow and use that technology is just fantastic.
What do you get with a multi-layer switch? At its heart, you get routing. Or routing, as some of you say. But with routing or routing, you get the ability to segment traffic that allows you to have more comprehensive, granular security, and the rich array of quality of service mechanisms that you spoke of really only kick in when you've got multi-layer capability. You've got a basic level of QoS with just layer 2 switches, but it's mostly just classifying and marking. But if you want really exotic queuing techniques to differentiate, say, between streaming and Netflix that might dominate your network because it's taking so much bandwidth, and being able to provide some limitation or rate capping with Netflix to ensure that your mission critical application gets through, the tool set you have with multi-layer at access, that's the way to go.
Yeah. Makes absolute sense. And then instead of going out through there, you're going to go out through these ones, right?
Correct. Yes, indeed.
And those lines, just those lines there, when we have these multiple connections, it's just for redundancy purposes, like you see here. You always have these multiple for redundancy purposes, right? If you're building a scalable network, that's how you're going to build it.
In a classic 2 or 3 layer design, you're building multiple uplinks primarily for redundancy. Remember, you spoke of earlier the protocol spanning tree. If you leave spanning tree to its devices, you're going to have one of those, say, 2 uplinks from an access layer switch being blocked. If you want to fully utilize those uplinks, then maybe we need another approach. And of course, this is where the potential with Campus Fabric comes in, where we can fully utilize those links.
Right. So virtual LANs.
Yeah.
We've spoken about this in one of the previous things. We don't have to spend a lot of time here. Basically, this slide, I like it because it kind of explains. So I think most people watching this particular episode or this course would already be pretty experienced or know the terminology, right? And they would be familiar with VLAN. But for those of you who are not, the term VLAN, it really stands for virtual LAN, right? A virtual network. So it's a network within a network. That's basically what you would call it. And the way that we've documented it over here is we've given it colors. So in an office, you would have different departments: engineering, HR, finance, marketing, whatever it is. And you don't necessarily want the engineering folk to be connecting to the HR folk, or and vice versa. And so you could either go and get individual switches if you've got lots of money, or take a switch. You've got 24 ports or 48 ports on a switch, one switch, and you'd say, okay, let me take that switch and let me segment them. So let me put all my blue users onto these particular ports, my yellow users onto here, my green users onto here. And that's kind of the idea with these, right? You have these, we can call them colors or whatever it is, but it's a way for us to segment our network. It's a way for us to increase efficiency on our network, to secure it in a certain way as well.
And to be a lot more scalable and a lot more adaptable. You've got a lot more flexibility when you virtualize the LAN. If you're dealing with classic physical LANs, which is the LAN you're on is determined by what cable you're connected to, it limits your ability to move around. If I move from one room to another room, I'm suddenly on a different LAN. Well, that might not suit me because that other LAN that I moved to might have a completely different security policy. But by virtualizing those LANs, I can distribute, say, the blue VLAN or the black VLAN or the red or the yellow or the white over multiple floors, even over multiple buildings, say, within a campus. And then my users can freely move from building to building, floor to floor, but still stay on the same LAN.
So a perfect example being a university, right?
Yeah.
A campus that we're talking about. A university just in Cambridge over here. I mean, there's, I don't know how many buildings that make up the university. So a student goes to one lecture, at this building, plugs in, and wherever they go, they remain on that virtual VLAN, on the virtual VLAN, right?
And indeed, the scenario that you've just described, where the VLAN is not determined by which port you plug into, but the VLAN is determined by how you authenticate. And we covered a little bit of authentication earlier, but once you say who you are and you prove you are who you say you are, so you're part of the engineering faculty, you plug into any port, the switch is intelligent enough to go, you're part of the engineering faculty, and it switches the configuration of that switch port, and that port now is
a yellow port or a green port or whatever it is.
Exactly.
Fantastic. And that was, I mean, when we talk about big steps in technology, like Intel processors, when they went from the 486 to the Pentium or whatever it was, that was a big jump, right? In networking, VLANs were a big thing, right?
Yes.
That was like a major jump, because suddenly it allowed us to take a simple network and just do incredible things that we weren't really able to do cheaply before.
And it came as part of the evolution of the switch. And remember, the switch evolved from hubs, where everything was just basically in one highly contended, one broadcast domain, one contention domain. With switches, you've got many, many benefits. Full duplex connectivity as opposed to half duplex. So many benefits. But one of the great benefits was the ability, as this slide alludes to, being able to tag Ethernet frames. And that tag, which is known as an 802.1Q from the Institute of Electrical Electronic Engineers, that tag identifies the VLAN that frame is part of. That tag is added at the point when the frame enters the switch. It can then travel around the campus, always saying, hey, I'm yellow, I'm on the blue VLAN, I'm on the black VLAN, whatever. And then at the point of egress or outbound port, that tag can be stripped. That basically means that devices...
Yes, it can be. Does it mean...
It doesn't have to be, but it
doesn't have to be.
Doesn't have to be.
So, meaning it could flow onto the internet with that?
Well, remember this is an Ethernet frame. Okay? So it's within that Ethernet world.
My bad,
It's within that Ethernet world, IP being the payload. But what it does mean is that if it is added at ingress, as it enters the network, so the switch port adds it, then it stays with it as it traverses that campus network and then is stripped on the outbound or egress. It means any of the devices that are connected to those switch ports don't need to even understand VLAN tagging or .1Q because they don't see the tag. It's only the network that sees the tag. It's a bit like you. Can I give you an analogy?
Yeah.
It's a bit like you walking into a customer site and you go to reception. And the receptionist says, right, identify yourself. You're Isaac. Okay, Isaac, yeah. And you're here to see Joe Bloggs. Gives you an ID card. You're an Ethernet frame, analogous to an Ethernet frame. You travel the building. That ID card allows you to go places within the building, but not other places within that building. When you leave, the receptionist or security guard says, can I have that ID card back?
Yeah.
Do you see?
Yeah.
That outside of the building, you have no concept of the ID card. It has no value.
Yeah.
Why would you retain that ID at the outbound side? Is maybe you've got a server, or maybe you have a router that needs to receive multiple frames on the same wire, but needs to be able to distinguish between this is blue, this is green, this is red, or I have a policy that allows you to go from red to green. Well, that means that interface that's receiving all these frames that are tagged needs to see the tag to be able to make that decision.
So if you had a university, let's say Cambridge University had a campus in Paris, for example, and they were connected. That means that if you're sitting here in Cambridge and you're on a yellow VLAN and you need to access resources in Paris, the router, you wouldn't have dropped the tag, you would have kept the tag. The router would know about that. It would route you off there, but it would respect that tag. It would keep that tag, and you go so that when you get to that side, you get access to the resources that you're allowed to.
Again,
would that be a use case?
It's a nice way of describing it. What will do the routing to Paris is going to be a higher layer protocol. This is going to be IP.
But the
router
tag
might say, right, anyone coming from the orange VLAN, I have a policy that says I can route that content, the payload, I can route that to Paris.
Got you.
But anything coming from the green VLAN, not allowed to go.
Okay, so we'll use the tag as a mechanism to either, it could do that. Okay.
It could be.
So one more question that I have on that would be, in an environment where, example, you're doing an update, you're updating. So maybe you had layer 2, now you've gone to layer 3 switching. Layer 2 would recognize the tags as well. But let's say you have a switch that's much older, a legacy switch, and it might not understand VLANs. You said that when the ingress comes in, it gets tagged. What happens if it needs to go to that switch and the tag's in the frame, but the switch doesn't know what to do with VLANs?
Well, it depends on the type of switch we're dealing with. Some legacy, very old switches that don't support VLAN tagging or .1Q tagging would look at that frame and go, that's odd. This is an oversized frame, because if you notice that VLAN ID tag, that .1Q field is 4 bytes. That would then create what is often called a jumbo.
Jumbo frame.
A jumbo frame, a frame that is larger than the standard 1518 byte length of an Ethernet frame. It'll go to 1522 as a minimum. And the switch goes, that's got to be an error. And it could well drop the frame.
Okay.
It could well drop the frame. Other switches could take a view and say, hang on a moment, I'm going to strip that out. And then I will pass that frame on untagged. And that frame will effectively be owned by what is called the native VLAN. In other words, the frame has gone native and now isn't owned by any particular configured VLAN, is just owned by a kind of catch-all VLAN known as native.
Okay, I understand that.
All networks, interestingly, modern networks support what is called native VLANs, which are frames on campus networks that should be tagged in some way or form, but happen not to be.
Okay. And that can happen. I mean, that's kind of, So it's just like a safety net for anything that doesn't have it go into here. This is where I'm going to put you. Maybe you're a lot more restricted, whatever, but you still get access.
It could be a misconfigured device. It could be a legacy device that shouldn't be there, that's doing this, injecting untagged frames. And you can then send untagged frames to what is called the bit bucket. Which is get rid of them.
And that's what we're talking about. That's what we're talking about over there. Okay, so this is the important thing. For those of you who want to know more about that, 802.1Q, IEEE, that's what you're going to look at.
Could I just very quickly say, if we break down that .1Q field where, which is 4 bytes, you first have a protocol ID of hex 8100.
Ether type.
Which ether type, because that's what Ethernet is expecting, and the next field is the type field. That says I'm .1Q tagged. Then you've got 3 bits, which are 802.1P. Now, some of your viewers here will probably remember .1P as one of the marking methods for layer 2. Layer 2 marking for quality of service. And that's
yes, of course.
802.1P. 2 to the power of 3 bits gives you 8 potential classes of service for layer 2 marking. Then you have an odd bit called the canonical field indicator.
I saw that. That's not used much.
It's always set to 0 now.
And then you color of your VLAN. Your VLAN ID, which can be up to 4095 or something.
96 technically. But a couple you can't use. So 2 to the power of 12 is another way of answering that.
Okay.
So, that's good.
All right, and then we see what basically we were talking about, right? Your data center, your servers, where your Exchange servers, your SAP, all of those things, and then the different campuses, but virtual private network using layer 3 virtualization. So virtual private network and encrypted data stream. We've covered this as well over a public internet connection. This is becoming, when I lived in South Africa, there was one telco in the country, and any connection, even if you had two buildings and you needed to cross the road, you couldn't even put a wireless from one side to the other side because they owned the road.
Yeah.
It was all highly, highly regulated. So the lease lines, we call them lease lines in South Africa, they were incredibly expensive because they could charge whatever they want.
Of course.
But today we don't have to use that anymore. We still do. There's massive usage for that. But today we use the internet to do that, right? We connect disparate offices right around the world, and we just use like a virtual LAN. We use virtual private network. Right?
Yes,
that's exactly what we're talking about over here.
Exactly right. And this is a particular use case, is the one that you've just described. When you want to traverse a network that is inherently or potentially dangerous, like the internet, and you want to keep the crown jewels, in other words, your data, your intellectual property secure. So you want to virtualize what was historically a private network, the classic leased line, but still traverse a shared infrastructure such as the internet. VPN is perfect. Uses a combination of a number of tools, encryption to hide your intellectual property from those that shouldn't see it. But you can also use a technique called hashing to prove that the person who sent it is the person who sent it. In other words, I know it was sent from Isaac to me because Isaac has embedded a special key which I know only Isaac knows.
Yeah.
And so
if anything changes, I know it's in transit, somebody has messed with it, right?
Someone has messed in it.
That's what we want to try and do.
A man-in-the-middle attack is another example where someone's got involved in between, say, you and me, modified some of the information, that then corrupts that key, and it means, hey, I don't trust it.
Yeah.
And these technologies all conspire together to create what is a private network, but virtualized.
Yeah.
It's by the way, one thing I will add there is today it's quite possible to run VPNs all the way across public infrastructures like the internet, but also across campus LANs, right to the endpoint, say a mobile device, etc. If you've got really sensitive information and you want that extra level of protection, then you can do what is called end-to-end VPNing. Very common. In fact, to be honest,
we have it on our computers, right? We need to connect to any resources at the office. Use the VPN.
Indeed, or even if you access most websites where there is some kind of e-commerce function, you'll notice that HTTP
automatically
changes to HTTPS. S means, hey, this is a VPN.
Yeah.
From your browser all the way to the web server.
Perfect. Yeah. Let's take a break. Right there.
Sure.
And then we will come back from this point onwards.
Good stuff.
Cool. Okay, Dave, we're back. Let's talk a little bit about the VPN technologies, right?
Sure.
IPSEC, I don't actually know if GRE is a newer VPN technology, but I know a few people, and they say, oh, they just prefer GRE. It's a lot simpler and lighter and stuff to set up.
They're correct on two parts, right? It's simpler and it's lighter, and it's, for certain use cases, is a perfect protocol to use. But one of those use cases that it's not good for is if you want encryption or you want any kind of level of confidentiality. For that, you've got to use protocols like IPSEC, which is a whole protocol stack providing confidentiality, integrity, authentication, anti-replay. What does GRE do? Well, it's still virtual private network, but it's not that private. It's really creating what is called a pseudo wire, or a virtual piece of wire between 2 points, where that virtual piece of wire is traversing, say, the public internet. Let's say, for example, I've got a router in one branch office running a protocol like OSPF, okay, dynamic routing protocol. I've now got a router at my head office running OSPF, and I want those two routers to create a peer relationship. But in between, I've got the internet. What am I going to do? Am I going to export all my OSPF routes into the internet for the internet to traverse only to then... No, absolutely. And I don't think the ISPs, the internet service providers, are going to be overly happy if you ask them to do that. But what we can do is we can tunnel across the internet, create this little pseudo wire, okay, a virtual piece of wire, copper wire, between the router in the branch and the router in the head office. And then those routers don't even see that there is the internet beneath. They just think they've got a piece of wire, an Ethernet connection, if you like, between the branch and the head office. And then those routers start exchanging routing updates.
And, okay, so I understand that, but wouldn't that be sensitive information that you would rather do over IPSEC?
Yeah, potentially so. So you could do it over IPSEC or IPSEC. You certainly could. But there's often, and as an engineer of a number of years, as you can tell, although I believe I've weathered well, not as well as you. Yes, indeed. There's always been occasions when I want a quick and dirty fix, just to test a connection. GRE is perfect for that. It's almost like you're carrying a virtual piece of wire in your virtual toolkit.
Just take it out,
just plug it out,
check
plug it in,
it all works.
check the connection, and then once everything's working, then maybe move on.
And that's open source as well, and all operating systems, everything does that. Okay,
absolutely.
Okay, so we got that. IPSEC, we know, is a framework of open security standards, and we're not.
And there's those functions I mentioned earlier.
Data integrity, authentication. What's this one? Anti-replay protection.
Oh,
anti-replay is like...
Yeah, just think if you went to your bank hole in the wall, the ATM machine, the automated teller machine. And
in the UK, they call it a hole in the wall.
Hole in the wall, yeah.
South Africa, a hole in the wall is what happens after they've cleaned out to the bank. You've got a hole in the wall.
Okay. But just imagine you go to that hole in the wall and you present your credit card, your bank card, and you say, right, I want €100, $100, 100 rand, whatever.
Yeah.
And you take that money out. And then the network goes, I wonder whether that's actually gone through. And it debits your account again, and maybe again, and maybe again. Replaying it.
So this is like, no, you can't do it.
If it's been successful, it's been successful, and then it's done. The transaction is done.
Okay.
So
there were a few times online in the old days where I've done it like, I wonder if this worked. I'm sure this didn't work. It's like, what? I've been charged 12 times for this.
But interestingly, by you doing it, that isn't doing replay as such. You're just saying, you're replaying it.
This is the system.
This is to make sure that the underlying protocols don't keep doing the same transaction, and you end up with, a bad hair day, as they say.
Well,
thank
you. Okay, MPLS. High level, because this is one of those things that there are people that specialize in this. This is their life, MPLS. and this is not our purpose, and we're not going to go here. Let's talk a little bit about MPLS on a really high level.
Let me just explain why MPLS. MPLS stands for Multi-Protocol Label Switching. And it's a technology that evolved from, in the early days, a protocol called tag switching. Now, the reason for this was IP routers routing IP packets were not the fastest things in the block. And there was a competing technology being developed by large service providers, large telcos, that was called ATM, asynchronous transfer mode. Bit of history now.
Yeah.
Now, these ATM switches could switch what were called ATM cells faster than any IP router could route an IP packet. And this was a threat to those vendors out there, those businesses out there that had invested a lot in the future of the internet protocol. After all, there's a good reason. Yes, ATM was a threat, but ATM was just quick, very quick at doing what it does, but didn't do a lot more in terms of value add. With IP, you have this rich array of intelligent services.
It was like a fast car just going around the track. That's all it could do, but you couldn't do your shopping.
That's all. Exactly. Great analogy. Whereas, you want air conditioning, you want leather, you want, music, ice, in-car entertainment. You get that with IP. So vendors got together, and vendors who had historically been in competition got together to develop this technology called tag switching. You introduce a tag, a bit like that VLAN ID. You introduce a tag which, when analyzed, that tag represents what is called a label switched path across a tagged domain that enabled those routers to route IP packets without having to examine the whole packet header and make a forwarding decision.
Checking it, check it out. Oh, that's
Absolutely.
where you repack it again.
It's a bit like you go into a nightclub, and what does the bouncer do when you first?
Most times it just throws me out.
Throws you out. Well, okay, yeah, I've heard. but when you go to the door the first time, you have to pay the person to get into the nightclub. Once you go into the nightclub, they tag you. Yeah, they tag you with a little.
Or they give you a bracelet that's always too tight, and you spend the whole night trying to pull it off.
But once you're tagged, any future decisions about whether you're permitted or denied access to parts of the nightclub or parts of the environment can be made really, really quickly. You're not told to every time you want to go from that part of the nightclub to maybe dance like your dad on the dance floor to another part of the nightclub. Oh, I'm sorry, you've got to go check with the reception.
Yeah, I understand.
And this fundamentally is what tag switching, which then evolved to become truly an open standard, multi-protocol label switching, was developed so that you could route IP packets as quickly, if not quicker, than ATM switches could switch what are called ATM cells. It was initially a technology developed to kill off ATM, and I'm not being controversial. That's simply the fact.
ATM switching still exists?
ATM switching still exists. You don't see it much. Certain specific niche use cases still use ATM. Great technology. Using some very advanced, what was called isochronous clocking techniques, which everything is synchronized using atomic clocks, etc. What MPLS allows you to do is leverage existing IP routers, but make them perform very, very fast and still also be able to leverage all of that intelligence, because they don't need to process a whole IP header to make a forwarding decision. They simply look at the tag. The tags are imposed at the point of ingress, a bit like we talked about VLAN IDs earlier.
Yeah.
And then and this is a lovely term, they're popped at the point of egress. You pop the label so that those outside of the MPLS domain have no concept that their packets have just traversed this MPLS network. Now, there are other benefits. One of the great benefits is that service providers can now allow customers to use what is called overlapping address space.
I've heard about that.
Yes. For example, you could have different customers that actually use the same part of the IP address space, but because the decisions made in the MPLS domain are not based on IP addresses, they're based on these imposed
That's
MPLS
really clever.
tags.
So so that's really clever.
It's very clever.
Because otherwise, generally, you would say, well, you can't have that because there'll be clashes of IP addresses. So you can have a short range of IP addresses, or just very few, and anybody, it would route it to the correct people.
Yes,
just because of that.
Absolutely. So you could have many customers, service providers could benefit from many customers, those customers sharing exactly the same IP address space, but there's no conflict, no overlap, because the IP address is not the primary component that's examined to make forwarding decisions. And this, therefore, gave rise to what is called an MPLS VPN. It's basically virtual pseudo wires across an MPLS domain, allowing different customers, even though they're using the same addresses, to have private connections, say between head offices, regional offices and branches. Company A would not conflict with company B, not conflict with company C, even though they're all maybe potentially using exactly the same address space. Powerful.
So is
complex.
All of the stuff is complex, right? That's why we're trying to talk about Fabric, which demystifies all of this. But is there still a place for MPLS today for large corporates? I mean, is it something that if you were to start up a new business today, and you had offices around the world, that you would still make use of MPLS today?
Many of us are using MPLS without even knowing it.
Okay.
Because you're connecting to internet service providers. Those internet service providers are connected to other internet service providers to create this thing we know as the internet. Much of the internet today out there, which we see as a cloud, is made up of lots and lots of MPLS domains linked together. And other technologies besides. But MPLS has been both a technological and commercial success. However, there is challenges around MPLS. It is inherently complex. It's not really a technology that lends itself to the campus. It's really a service provider technology. There are some exceptions. If you're a very, very large enterprise, you may choose to run MPLS in your own campus environment. But for the most part, most customers of service providers themselves wouldn't use MPLS.
But in the background.
But the service provider will use MPLS.
And this is what you were referring to, which if you just know IP, this blows your head, right?
Yeah, absolutely.
Like,
Look at that.
Supposed to work.
How can that happen?
It can with MPLS. We don't want to go. I don't want to go much. Much more on that, and we'll just kind of summarize that. I think that was a good explanation of MPLS. It's never something I've read a lot, or I've read over the years about MPLS, but it's always kind of one of those things like you start reading the introduction and it's like, Netflix. Yeah, it's like Netflix is better than this. This is going to hurt my head. So I've never really got into it, but like you say, it can be incredibly complex. But on a day-to-day basis, you and I probably never touch it much. But if you work in ISPs, it's probably something that you're going to.
I think any of your Academy viewers that might be interested, if you are pursuing maybe a career with service providers, MPLS is something certainly worth reading up on. But to truly understand MPLS, you also need to understand routing protocols like BGP, the Border Gateway Protocol. As the two, BGP supports MPLS. They work hand in hand to create what are called label switch paths between one customer and another customer. BGP is actually being used less as a routing protocol and more as a simple messaging service to exchange policies between customers of this MPLS service. So the two go in hand.
And we get to that, right?
Yeah.
Layer 2 networks, they fast, we know all the benefits. We've covered that. We've covered that already, but they don't scale, for the reasons traditionally that we know about. Layer 3, great. They do all these wonderful things and they connect us to the outside world. So these, I would screenshot this if I were you, because this is an important thing, and you might see exam question around this. But I think it summarizes exactly what we've done. There's a lot of stuff here. Each one, my recommendation to you is, if you read any of these and you don't understand them, it's not just Academy. I don't have all of this stuff on Academy, but it's worth your while to go and do some research, to understand, why. Because what we're trying to do with this lesson, and possibly the next one, is we're showing you that the internet is the network of networks, right? And it's connected, and in our little home we connect, but behind that there's an ISP, and behind that is hundreds of ISPs, and your message needs to go through hundreds of possibly potential routers before it gets to its destination. Maybe not hundreds, but and these things are complex. All of this stuff is complex, and this is what we're now going to try and do. You look at all of this complexity, and it truly does hurt your head. It truly is a challenge. So let's now start looking at how we simplify this, because there must be a better way. Like everything else, people work with this stuff, but there's always somebody that comes along with better technologies, better ideas, and that's what we're going to be looking at now when we look at this. So let's take a quick break, and then we'll come back to this.
What is the biggest responsibility for a leader? That is to give the market a vision. Tell the market what is happening, how it is happening, help them wrap their minds around them, and then guide them through that journey. And that starts with the customer. So let's spend a moment in the minds of these customers, whoever they are, whichever industry, whatever level, from a network admin to a CXO, they all are trying to grapple with this post-pandemic world. A world that has fundamentally changed. Why? Because the needs of the people have changed. You, me, all of us, we are living lives differently. We shop differently. We go to school or educate differently. We get healthcare differently. We go and get services from our government differently. We live differently. And therefore, every business out there must change to cater to this demands, this change in demands. And what are they grappling with today? Whoever you are, you're thinking, well, now I need to reach my customers, my patients, my students, my workers. I need to reach them wherever they are. I need to make sure that I can provide them experience wherever they are, which is very similar to if they were in the office or in the hospital, in the clinic, in the school, in an office. That is what is top of the mind. And you're thinking, how do I do this? How do I scale? Not just scale my network, but scale my team, scale my talent, scale my processes. This is the context. This is the surroundings in which a leader like Extreme has to come forward, give a vision, and then show the path. But guess what? These are not the only things that are challenging the customer, because there are other things that have always been there. For example, there always been too much technology, which is too confusing. A lot of customers essentially say that, yeah, you show me a slide, if I could magically switch to that slide tomorrow, everything would be great, but I can't do that. Why? Because I have my own constraints in people, in time, in talent. And then eventually the quintessential question, is it all safe? So what are we doing as leaders? We, first of all, give our commitment, always have, always will, to our customers that we are reducing complexity. We will give them solutions that bring them to their outcomes in their way, at their pace, and we deliver trust. But in this post-pandemic world, the vision to help wrap our minds around it, help their minds wrap around the situation, that vision is the vision of Infinite Enterprise. 3 outcomes that all of us need to deliver. Number 1, we have to be consumer-centric. Why? Because whoever we are, our consumers are changing, therefore we have to change. And we have to learn why they're changing, what their change requirements are, and act on that. The second is our users, our consumers, our customers, they're all distributed. Our students, our patients, they're distributed. So we need to reach that level of distribution. We need to make our enterprises infinitely distributed, and we have to do it at scale, not just the scale of the network, but scale of the team, scale of the talent, and so forth. Now, this whole thing is our vision and our commitment. And yes, there are others who are saying something similar or some portions of it. But once you have something to say crisply and then deliver it with proof points, that's what makes you the leader. So this Infinite Enterprise, while it is a journey towards their outcomes for our customer, this is our North Star. Every investment that we make, everything that we do, every new resource that we bring in, it is meant towards that North Star.
Okay, now we're going to be talking about jumping into fabric, extreme fabric. You'll hear different vendors use the term fabric.
Yeah.
Extreme, you often hear us talking about this campus fabric, extreme fabric. But let's jump in and see what all the noise is about. We've spoken about spanning tree protocols, right? And the idea is to eliminate this problem that you get of creating loops on layer 2 networks,
broadcast
right?
loops, all that.
BGP, version 4, OSPF version 2, all of these things leading to complexity, right? Complexity, making networks more and more complex.
It's a bit like it was all designed by a committee.
It was.
Which ostensibly it was.
It was.
Yeah.
There's something that I want to call out here, and I want you, David, just to chat a little bit about this. This term, it's not the only way. There's other terms for Mac in Mac, right? But can you talk a little bit about what Mac in Mac encapsulation is about?
Remember, one of the great benefits of Layer 2 is it's fast and it's simple. So if we can get as much intelligence into Layer 2 without overly complicating matters, surely that's got to be good. And that really is at the heart of a shortest path bridged network. Now, shortest path bridging, by the way, is what campus fabric really is. Because you're right, the term fabric is used by lots of vendors to mean different things. At the end of the day, a fabric can be thought of as purely a network. But what we've got here is a network designed specifically for campus environments. And by campus, that could extend out to data centers as well. That leverages as much as possible the benefits of KISS, keep it sweet and simple. How? By taking MAC, Media Access Control layer, Ethernet ostensibly, using that to transport traffic from end to end, carrying the original Ethernet frames generated by the customer traffic. So you're putting effectively an Ethernet frame that the customer provides or the customer is using to carry its own payload, whether that's IP or whatever it might be, whatever payload, and putting that Ethernet frame in another Ethernet frame to traverse. Do you remember I was talking about pseudo wires?
Yeah.
It's a bit like creating an Ethernet pseudo wire across maybe quite a complex infrastructure, but you're abstracting all of that complexity by simply presenting a synthetic piece of Ethernet cable. Instead of having to traverse hop by hop by hop by hop, which is actually going on underneath the covers, you're actually connecting from one part of the, say, campus to another part of the campus across this pseudo wire. We do that by taking media access control, an Ethernet header with its payload, and then placing it into another Ethernet header. So that
so we take the whole frame,
drop it in,
and then we drop it into another frame.
Drop it into another frame. Do you remember we had IP over IP, and maybe we secure it with IPSEC, or we add additional pseudo wire capabilities by using generic routing encapsulation, which was the simpler approach. With Mac in Mac encapsulation, we're doing something not dissimilar to GRE. But in this case, we're simply taking an Ethernet frame and placing it inside an Ethernet frame. Hence the term Mac inside Mac.
That's nothing to do with cheeseburgers.
I was going to go there.
Mac in Mac. And so for a switch that gets one of these frames, it's irrelevant. It's just an Ethernet frame. That's got a Mac header. That's it.
Absolutely.
So what you're doing over here is, if you have a complex network with lots of sites across a country, for example, a city, if all of those are connected, it's almost like if A wants to send a message to B and B is on the other side of the country, it's almost like you would have just a long Ethernet cable and it's going from one side to the other side.
But you virtualized. You virtualized that long Ethernet cable. And you kept things really, really simple. It's not limiting you in terms of what you're ultimately carrying in terms of the payload. You still got your original Ethernet frame carrying whatever protocol you want.
Your video, whatever.
You want video support? Easy. You want full IP support, connectivity? Very easy. But what you're doing is you're ostensibly placing that Ethernet frame carrying the payload that you want to carry and then placing all of that becomes payload to an Ethernet frame that's going to allow you, as you say, to maybe traverse a service provider core network. It's there's a number of techniques. Mac is one. Q is another, where you put a .1Q tagged Ethernet frame inside a .1Q tagged frame. Again, doing a similar kind of job. The benefit, the second point, or second bullet there indented, removes the current MAC address scalability limitations because you're suddenly expanding the number of endpoints that you can support with traditional MAC address semantics. Separates customer versus backbone demarcation. Absolutely. The customer has an Ethernet frame, gives it to the service provider. The service provider says, thank you very much, puts it inside their own Ethernet frame, Mac in Mac, and traverses the core network. Goodness me. Sounds a little bit like MPLS.
Yeah.
But without the complexity. MPLS requires not just an understanding of MPLS, understanding of BGP, understanding of routing protocols. With this, there's none of that complexity. You're basically taking all these dependent protocols that historically you needed to achieve the job.
Like OSPF
and all that multicast, like protocol independent multicasting, and there's so much more besides. I think we've got a slide later that kind of illustrates this. We can get rid of it all and just go for a simple layer 2 shortest path bridged network or campus fabric. It's designed from the ground up for virtualization. It truly is. And at its heart is the principle that pseudo-wire is ostensibly a VLAN dedicated, a backbone VLAN they call it. Remember the term backbone from how we scaled campus networks earlier?
Now the virtualization thing, now it's sinking.
Virtualize that backbone. Yeah, indeed. And it's a lot, I've got to say, one of its greatest virtues is it is so simple. It truly is. It's like moving from, a car.
So it's difficult to understand, but simple to operate.
Very simple to configure. To configure a campus fabric, certainly on extreme boxes, a couple of configurations.
Yeah.
And that's it. As long as the switch supports it, it just happens.
So
it's a joy to work with.
Yeah. I like that phrase. It's a joy to work with.
It really, truly is. Once you've got over that initial challenge of conceptually it's working in a different way to the kind of traditional protocols that we're all brought up with in this world of networking, in that sense. But
so you would say that there's a learning curve to understand, because I mean it's still complex, right? I mean, there's still some concepts over here that you have to go and do some chewing and reading up on. But what you're saying is, once you've got over that, implementing what you've learned then becomes really easy. And by reference, then managing it must be also quite easy.
Yes, indeed. I mean, I think in an earlier module, fundamentally what Mac in Mac encapsulation is providing is what is called the data plane. It's how you shift data from one part of the network to another part of the network nice and quickly. But what you've got is the separation of the data plane from, and you covered this earlier, I think in an earlier module, the control plane.
Yeah.
This is where a certain amount of complexity might come into play. Is there is an expectation that engineers working with Campus Fabric will have some understanding of the control protocol that's used, which is a protocol that is not dissimilar to OSPF.
IS.
Intermediate
system.
Intermediate system, yes.
Yeah.
A protocol that's an open standard that actually predates OSPF, interestingly. It's been around a long time, originally developed by the DEC Corporation, which was then acquired by Compaq and acquired by HP. It is an open standard. It's a protocol well known in the service provider community, less well known as a routing protocol in the ordinary sort of business community, if you like, the ordinary sort of client environments. It's much easier to get OSPF skills, for example, than it is to get ISIS skills. With that one proviso, the market that really loves this technology is the service provider markets as a way of, in very simple ways, achieving everything that kind of MPLS networks achieve, but without the expense and complexity of rolling out MPLS support. Which, remember, MPLS on its own, no, you've got to know so much more. It's not an easy protocol stack to work with. This, in relative terms, is so much simpler.
Excellent. So let's go.
This is a great slide.
Yeah, let's go to this one, because here we can see what these are all just protocols, right?
Yeah,
I mean, these are just
VLANs, OSPF, PIN, protocol, and that list is not exhaustive. Goodness me.
Yeah. And so we take in all of these protocols that have been used to route, like you said, traffic from one location to another, and all of these, plus maybe even more. And what we're trying to do with Fabric is we're trying to reduce that all to one protocol.
Basically one protocol for the data plane, and then an additional protocol, one more, ISIS, for the control plane.
All right.
And
let's go hit the we recorded this earlier. Let's go hit the light board, and we can do something with this particular slide that I think that will make it come alive.
Good call.
Okay.
Well, in the previous slides, we talked about how shortest path bridging MAC or SPBM is simple. I just want to illustrate how simple it is by, say, comparing the past and to some extent the present, i.e. our classic three-tier hierarchy that we spoke in the previous section, and the Fabric Connect environment of the Enterprise Campus Fabric, and how simple this is, just to illustrate. Okay, what have we got here? We've got at the bottom what we call the access layer. This is where we have our users, our devices, our PCs, our laptops, anything hanging off the network at the access layer. Some of you in the audience might refer to it as an IDF, the IDF area, Independent Distribution Frame. Now, to provide connectivity, I need a protocol to support that. So let's start with the logical link control protocol, which is 802.1. Now I need 802.1. Thank you. So this symbolizes the first protocol I'm going to use to start to build this three-tier classic traditional hierarchy. So let's get some connectivity in place. And we need some redundancy also in place. And then we go from the access layer out to the MDF, otherwise known as the distribution or aggregation layer. Again, we spoke about that earlier. One of the challenges that we have around here, of course, is the very real possibility of loops. Now, we've spoken about this already. Loops, Ethernet, loops, they don't work together. So what we need to do is break those loops. And we do that with another protocol that, again, I, as an engineer configuring all of this, need to be skilled up in. And that protocol is the spanning tree protocol. And here we go. So far, I've got 802.1. I've got the spanning tree protocol. Let's just, for reference, write these out. So I've got 802.1, and then we have the spanning tree protocol. 2 protocols so far, but we haven't yet fully built this environment. We need to get from the access through the aggregation distribution and out to the backbone or the core. Possibly that's where our firewall's going to be, and that's certainly where the outside world is. So again, we need to build some connectivity in at this point, and we also need to build some routing logic at the aggregation layer. For the routing logic, we need routing protocols. And a good routing protocol? I don't know. Name me one. What about OSPF? Give me OSPF. Thank you. Can you see what's happening here? I've got 802.1 giving me logical link control. I've got spanning tree protocol for loop avoidance, and now we've got our routing protocols, OSPF, and that's if we choose to use OSPF. You may have other routing protocols that you need to manage as well. Now notice that we also have users, and I've marked these users out in different colors. Well, 2 colors here, pink users and green users. And they're there to denote virtual LANs or VLANs. VLANs, yet another set of rules to define how messages are to be handled. Thank you. Goodness me, can you see that we're getting a real stack going here? I've got 802.1, I've got spanning tree, I've got routing, which allows us to then leverage these VLANs for things like policy control, inter-VLAN routing. Again, we spoke about this in a previous set of slides. So far, so good, but we might need policy that says those in the HR department are allowed to communicate to those in the accounts department, or those in the accounts department can't speak to those or share resources from those in, say, HR or in marketing. So we're going to leverage these VLANs, which provides us that segmentation, but we're then going to have some access control. If-then statements of condition. Does this frame come from the HR department, going to the marketing department, carrying this application or that application? Yes, it is. Permit or deny. Those policies are built into ACLs. ACLs, yet another protocol or a set of protocols that we need to be mindful of. Can you see what's happening here? We're building a stack of protocols. Each of these protocols we need to have the skills to understand, to be able to configure, to be able to manage, to be able to report on. And handling things like moves, adds, and changes can be really quite traumatic. Let's build those ACLs in there. So we have access control lists. Yeah, quite a stack growing, wouldn't you agree? And then what? Well, there's the outside world. Let's put a big fluffy cloud out there to denote the outside world. We need to get out there. How are we going to get out there? Again, more protocols that we might need to be skilled up in to understand, to handle, certainly to accommodate those moves, adds, and changes. Protocols like, I don't know, BGP. Give me BGP. Thank you. And protocols like, well, it's all dependent on the service providers. Maybe MPLS. Maybe Lisp. Maybe Trill, and maybe so much more besides. Thank you. Yes, goodness me. Okay, I think we've got the point. All of these protocols I would need to be able to understand, be able to configure, to be able to even handle some of the even quite small moves, adds, and changes. That is a lot I need to be able to understand and configure. Well, what about this world over here? Again, I've got the same connectivity requirements with Fabric Connect. The whole thing's based on Ethernet at the end of the day. So let's build that connectivity in. Lovely. And to be honest, I could go connections like this. Whatever's necessary, whatever I want. I'm free to choose whatever kind of topology. It's completely topology independent. Doesn't need to be 3-tier, doesn't need to be 2-tier, doesn't need to be spine leaf. Whatever topology, it's wholly topology independent. Any configuration, say, of these green VLAN users, pink VLAN users. Hey, no problem. This is all standards based. It's based on standards. Ethernet based on standards like IP. The big difference, whereas over here, I have to configure all these individual protocols to accommodate any move, any add, any change. Here, if I have a move, add, or a change, I configure at the edge. I simply provision at the edge. Here, on the right, on this side, with the traditional 3-tier, I have to configure here, 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 out there, ensure my SLAs with my service providers are correctly written and that we all dovetail together. Over here, a real simple approach, Fabric Connect, shortest path bridging, MAC in MAC. Let's just spell that out, shall we? Shortest path bridging with a small m to denote MAC in MAC encapsulation. Really simple, quick time to value. Security is part of this Fabric Connect solution, as we spoke about in the previous slide. It's actually built in rather than here, where security is often seen as very much an afterthought, which you have to accommodate with protocols like VLANs and ACLs and so much more besides. I'll tell you one big point I want to make here. How many protocols am I listing? 1, 2, 3, 4, 5, 6, 7. And that's before we get into all those WAN protocols where those bricks were thrown at me, like the Trills, like the Lisps, like the VXLANs. Over here, just one control protocol. And that protocol is, drum roll please, ISIS. Give me a bit of ISIS. I thank you. One protocol to be concerned with. One protocol that every time you provision anything, any move, any change at the edge, ISIS takes over and programs the fabric to accommodate for that change. No requirement for engineers to go out and make configuration changes on all these various boxes that make up the fabric. Compared to this, I know which one I'd prefer. Yeah, the simplicity, a single control protocol with shortest path bridging, MAC in MAC, otherwise known as Fabric Connect, versus the traditional 2-tier, 3-tier, based on a whole series of what are effectively patches to an inherent design weakness, a weakness within Ethernet, the protocol itself. You could argue, in fact, that what we have here on this side is Ethernet fixed. In other words, Ethernet where the problems have been fixed.
So this is what we were talking about earlier, the MAC and MAC encapsulation. As you see over there, the payload, the source MAC address, the destination MAC address, and if you have VLANs, of course, there's the 802.1q. So this is what you're doing with it. You are adding all of these into this, right?
Yeah. Effectively, what you see on the left-hand side, either tagged with .1q or not tagged, depending on whether the customer is supporting VLANs. That is then, typically passed to a service provider. So there you can see a direct mapping. We've got the payload, we've got the customer VLAN ID, CVID, we've got the source address and destination address. Nothing's changed there. Then you add a 24-bit service identifier because Fabric is capable of supporting a whole variety of different services, whether it's unicast, whether it's multicast. Sure. In fact, your imagination is your only constraint because you've got 24 bits to play with.
It's a lot of stuff.
Yeah, 2 to the power of 24 is what? 16.7 million potential services that... So can you see from a scaling point of view, this starts to become interesting for service providers as they creatively think up additional services that they could offer their customers. Then you've got, and this is the interesting bit, you've got the pseudo wire. You've got the start and the finish of that pseudo wire, that I've been mentioning previously. So that's the backbone service address, and the backbone destination address. And then that pseudo wire has to have an identifier. Well, that's a bit like a VLAN ID, and that's the backbone VLAN ID, or BVID.
This guy, yeah.
As you can see there, yes.
Yeah. That guy there.
That's there, as you can see.
This guy.
That's it there.
So that's the equivalent of a VLAN tag, if you want to call it that.
Absolutely.
So all traffic that's going through the fabric then is identified by that, or you know from the tag now where it's coming from.
Absolutely, yeah, indeed. So you can think, right, the start point, destination, source, the start point, the backbone source address, destination, the backbone destination address. You've got which pseudo wire you're going to use to get between those source and destination addresses. And then the ISID, as it's often referred to, is what service you're carrying. Now, a service could be one customer versus another customer.
Okay.
Yeah? One example. Or one customer's multi-cast traffic.
To the power of 24. Lots of customers.
To the power of 24.
So in VLANs, you're limited to 4,096 VLANs. Do you have limits here?
You will have by whatever the address space denotes.
Okay.
It's always 2 to the power of however many bits you've got to play with.
Okay.
So you still have those kind of limitations. Backbone VLAN IDs, there's no real requirement. Most service providers support 2 backbone VLAN IDs that will support customer-to-customer site traffic. Just 2 is required. And that can be used, A, for peace of mind, redundancy, should one go down, but also for performance. Because the wonderful feature of this shortest path bridging is there's no need for a spanning tree for loop avoidance. You can fully utilize those
every single
virtual uplinks.
Everything that you've got.
Absolutely. You can fully utilize it. So you get a performance gain and a peace of mind gain. What I refer to as kind of the balance of the P's. Yeah, peace of mind and performance.
And it's not an incredibly expensive technology?
No, not at all. Not at all. And again, available on a whole variety, certainly in the Extreme portfolio, on a whole variety of different switches to suit particular markets and particular use cases.
One
so there we go. These are the kind of
services.
Yeah, look at these. Your layer 2. You want to send layer 2 traffic across. You want to send layer 3 traffic across. You want to send IP multicast traffic across. You name it, you've got it. Even the last one there, you just want to send native IP routing protocols across the fabric. No problem. Ooh, that sounds a little bit like GRE. But again, we're not doing GRE here. But we're simulating that sort of GRE world by allowing maybe 2 routers either side of the fabric to be able to peer across what they see as a pseudo wire.
So you've got fabric, you can basically chuck anything across.
Ticks every use case. And it's a proven, mature technology founded on open standards.
Massively scalable?
Massively scalable. And crucially, easy to deploy. Look at the status quo versus, say, Extreme fabric approach. And, yes, Extreme do it. There are other vendors that do it. But you can see with, the classic approach, you've got hop by hop provisioning.
This being the classic approach that you have to do
side.
Yeah.
Hop by hop provisioning. You need to reconfigure the core every time you have a move or an add or a change or a deletion. Because there's a lot of manual steps in the step-by-step or hop-by-hop configuration, prone to errors.
Human errors, yeah.
No, and the services and the policies associated with the services are irrevocably tied to the underlying topology. So you're very much topology dependent. With Fabric, you simply issue a command at the edge, start the Fabric, and voila, as long as the core is in place, everything will configure courtesy of that control plane ISIS that we mentioned earlier, intermediate system. As long as that is there, already configured, you can simply provision at the edge like that. The core is completely hands off.
How much ISIS do you have to know to be able to do this efficiently?
From a customer point of view, very little.
Okay.
From a service provider point of view, you've got to know ISIS. Yeah, you've got to know. But I've got to say, if I'm honest with you, Isaac, ISIS as a protocol, I find a lot easier than OSPF.
Yeah.
Truly, OSPF, there may be more of it out there, but it's a complex set of patches, in my opinion.
Well, there you go. If you want to make a career of using Fabric and setting up Fabric, it's worth your while getting to know ISIS.
Yes, absolutely. And here we have the ISIS focusing in on the control plane that is ISIS. It has a lot of similarities to OSPF. What we're looking at here is we're looking at life from the perspective of the service provider, where they're building that control plane, which in turn will then support those backbone VLANs that will in turn support through MAC encapsulation customer traffic. From a customer point of view, a couple of commands provisioned. As long as
sounds almost like magic, huh?
Absolutely. Wonderful thing about ISIS, really rapid conversion. So if the core network, the service provider network, should have certain failures, no problem. The customer backbone that are using those backbone VLANs, completely unaffected, because ISIS will very rapidly
like
reconverge.
300 milliseconds or something.
No, it's ridiculously quick. And
that's got to be. I mean, this whole course is about building scalable, and redundant networks.
Yeah.
If you're a service provider, that is at the heart of the thing. I mean, to be able to, just recover like this. Really,
absolutely,
really
absolutely so. It's.
Well, we know some of the stuff, right?
Yeah.
We know those. We know Dijkstra, forwarding entries, forms adjacencies to the neighbors. We've spoken about that before. Let's end on this slide for this particular session. We've covered a lot in this session, and there might still be a couple more slides that we need to do. But let's finish on here, and we'll land this week's episode, and maybe we can convince the powers that be to bring you back for a couple more.
Okay.
And
that would be my pleasure.
In the next episode, that would be fantastic.
Well, Fabric Connect, that is the core technology that we're referring to.
Yep.
The backbone VLAN IDs, the ISIDs, etc. That is the core technology. And you've got to have switches that support Fabric, okay?
Sure.
Of which there's an extensive portfolio from very relatively simple switches to powerful, fast switches, and
so would you need them on the edge, on the aggregator?
You'd have them on the edge and in the core of the network to build your Fabric.
Okay,
yes,
I understand.
But you could be out there and you say, well, I want the benefits of Fabric, but I don't, or not all my devices, not all my infrastructure devices support Fabric. Is there a solution? Absolutely, there is. It's called Fabric Attach. As it says there, enables non-Fabric devices to participate in the Fabric by automatically attaching users and devices directly to Fabric services.
So that's a big one, right?
Absolutely.
Because not every customer is going to go and just say, replace my whole network, do everything. They see the benefits. We want to go and do it, but with Fabric Attach, now we can take non-Fabric savvy devices and connect them into the Fabric and get the benefits.
Absolutely. As the title of this slide says, extending the value of Fabric Connect through Fabric Attach. Yeah. The value of Fabric Connect is the value of Campus Fabric.
Even if it's not
out to non-Fabric environments.
Even if it's not extreme.
Even if it's not extreme, absolutely. They don't all have to be purple, Isaac.
Let's leave it there, because that's a fantastic thing. David, thank you so much for sharing with your great knowledge with us. I sit here and I'm like a sponge, I'm absorbing. And I think a lot of people who watch us are exactly the same. So thank you so much. I really appreciate it. Hope we can see you again on the course, because I think that there's still some more stuff that you can just help unravel for us. Thank you.
Anytime. Again, my pleasure.
Thank you, sir.